Alright, time for another draftphysics.com, debatephysics.com, also video presentation. So, a bit further away from the mic, so I'll probably have to adjust the volume on this video, but anyway. So, lever. So I've been sitting here for an hour or so, just contemplating and saying, what is it? Why is it that this is so convincing to me? And you remain so unconvinced. So we have a 1 mass, 2 units of distance from the fulcrum, 2 mass, 1 unit of distance, and it balances perfectly. So it's suspended from above the lever. That is, the string doesn't go around the bottom, it's suspended from the top. So no weight is supported from the bottom of the lever. The weight is supported from the top of the lever. And it's a really important, I mean, it's a little tiny detail, but it makes a huge difference in terms of being able to maintain an oscillation. So if you suspend it any other way, it might oscillate a couple of times and it'll stop. But if you suspend it from the top, the energy will just keep switching back and forth. And what's really happening is just a little tiny bit of the lever's mass. Every time one side goes up, it's basically swing some of the mass from the other side to its side. And now it's a little tiny bit heavier. And so that's why, it's getting heavier and heavier. The more one side goes up, the heavier it gets. So obviously it stops doing that and swings down and overshoots, and then the other side goes up. So the energy stays in the oscillator. And the trick is, you can see there's a little tiny bit of motion, because unless you do it exactly proportional, that is, all the energy you put in is completely symmetrical on both sides, it will process in all kinds of ways. So I can't just push it with energy without causing it to start moving in the direction I'm adding the energy, because I added it just to one side. So if one side had more kinetic energy, so to speak, then it would start to process wildly. So it's a way of testing the fact that, yeah, it really is equal energy. The 2 mass going 1 velocity, same energy as the 1 mass going 2 velocity, because all I have to do is have a tiny bit of eccentricity and it would start to process wildly. So I have to put the energy in equally on both sides. If there's any more energy on one side than there is the other side, that extra energy will cause that side to swing out further, and it'll cause an eccentric procession. So it's obviously the same energy to move this as it is to move this. 2 mass 1 velocity, same as 1 mass 2 velocity. Then you can just sit here and watch it and say, yeah, they're okay. Makes perfectly good sense. It's a complete physics theory. And you're saying, why do I need to bother with some notion that lighter mass has twice as much energy? That it's somehow doing twice as much of something. When it's clearly balanced, the symmetry is perfect. And then I can illustrate even more clearly. Okay, so the trick is when I lift this, these masses are irrelevant. I'm not feeling either one, because they're counterbalancing each other. They're perfectly balanced against each other's motion. And so it feels like this doesn't weigh anything at all. I can lift it and it's like I can't even feel it, because the only thing I'm lifting is this hollow aluminum tube. These are magnets, and they're sticking to each other, not the aluminum, obviously. So I thought it was steel when I put it together. I said, oh, it's just a nice piece of steel, I'll use that. And it just turned out to be aluminum. So it's incredibly light. So the magnets weigh probably as much as this bar. But the point is moving this way, I can feel the weights. But moving this way, not so much. Yeah, nothing. And so the point being is that I could probably increase these weights and say I could put a 1 pound here and a 4 pounds over here if it was a strong enough piece of metal. And that's all I'm going to really feel, though, is the weight of the metal. All I'm really lifting is the lever itself, because these weights are completely counterbalancing. So no matter what weights I put on it, I won't feel the weights doing this. I'll just feel how much of that lever did I move. I'm just feeling the weight difference between the lever being on that side and the lever being on that side. And that's all it's switching. It's just moving, like I said, you can sort of see the line. It's just moving mass to the side that's the highest. That side is the mass is moving from the center of mass of the lever. And so there's no there's nothing else happening here. The only energy is that little bit of mass switching sides, and that's what's falling in the gravity, so to speak, is that little bit of mass that's switching sides. So that's the oscillator. That's the motive force behind the oscillation, is that little bit of mass switching sides, and this is irrelevant because these two are canceling each other. They're counterbalancing each other. They're counterweights. So I was thinking about, well, I've had lots of thoughts. I was saying, okay, if I put this in a stream and put, little pieces of stuff at angles, I can make it spin, right? Or I can put it in the wind, make a propeller, make it spin. And we can't make something spin in gravity. So I'm sort of arguing that gravity is essentially the same kind of mechanism. There's a force that's pushing on all of this, keeping it this way. So I could keep it balanced in a stream. I could keep it balanced in the wind, by putting the sails at the right places, the right size. And I could create a balance, and it would just sit there and wobble in the wind. And obviously I can do even better and make a propeller. And why is it possible, that this reign of gravity, I can't make a propeller out of it? And the reason is because I can't reflect gravity. I can make a propeller in wind, and I can make a propeller in water, because the water bounces off the propeller. It doesn't get absorbed by it. It bounces off. It goes around. And gravity doesn't do that. Gravity doesn't hit this and bend off of it and bounce off of it and deflect or do any of that. It goes straight in, straight through. And so there's no, until you find a way to reflect gravity, you can't make a propeller. Fun fact, I don't know how important that is. It's just something I noticed when I'm thinking about it. What's the distinction? So, but otherwise, you can make analogies to stuff like wind and a stream, and you'll get the same results as you will in gravity. So some things I do, if I just push it this way and let it oscillate back and forth like a pendulum, well, now the masses are moving the same speed, So now they're duplicating what they do in gravity. But as soon as I start to oscillate it or rotate it, they're moving very different speeds. So that's another key. Get it quiet. So there's no real way to lift this up. You got to be really careful to keep it completely centered and then release it so you don't get any unwanted oscillations, because it moves so freely and so easily. So I'm just sitting here watching this and saying, okay, so why doesn't this convince people? You have a one mass moving two velocity, you have a two mass moving one velocity, it's perfectly balanced, it all makes sense, the momentum is conserved beautifully. Why would I mess with that perfection? It's so complete, it's so easy to understand what's going on. gravity's a constant force. It's essentially just saying you have a small mass, a small boat with a small sail. You have a big boat with a big sail. And it turns out that the big boat collects more wind. But it's got to collect more wind because it's got a bigger boat to push. And, it works out just fine. Makes perfectly good sense that they would move the same speed in gravity because they're basically doing the same amount of stuff. One's collecting it, and you'll see it when they hit something, even though they're moving the same speed. When the big boat hits the shore, it's going to have twice the energy, whatever size bigger it is, it's going to have that much more energy. And it's always going to be momentum. When it hits the shore, it's going to be a weight. And that's what this is. This is weight. So even though this is less mass on this side of the lever, there's less mass. It weighs less. If I put just this side of the lever on a scale, it weighs less. So it's less mass. But, configured this way, it weighs the same. Okay, so the collection is the same of the force. And you have to move this twice the velocity that you have to move that. And the mass is half, and it makes perfectly good rational sense. So if I do spin it, then obviously if I spin it on its, I didn't spin it on its center, so you have to spin it, and you have to make sure, again, if I hit it from just one side to try to spin it, right, it's processing all over the place because there's more energy on one side than there is the other side, obviously. And so the same is true if somehow these things weren't equal in terms of the energy, then there's no way I could spin it on a center. It just wouldn't ever happen because it would automatically start processing. And so how does this in any way indicate, this has got twice the energy here. This one over here has twice the energy. And then what would happen? Again, if I stop the lever, what am I going to feel? So if these magnets could fly off, that is, they were just free, they were just getting pushed, and then I just stuck my finger in to stop the lever, what am I going to feel? I'm going to feel almost nothing. Because the only thing I'm stopping is the lever. I'm just stopping the piece of aluminum from moving. So it's only that momentum I'm going to feel. So that's a tiny amount of energy, right? And the weights are just going to fly off going the speeds they were going. So say if these weights were 10 times the weight of the lever, you're talking that more than 90% of the total energy of the lever will be leaving the lever. And the two mass is going to be going one velocity, and the one mass is going to be going two velocity. No doubt about it. There's not going to be any evidence that kinetic energy, that there's twice as much energy coming off one side of the lever as there is coming off the other side. There's no way to rationally believe that. So it's a lopsided. Yeah, but it's that's fine, right? So it's oscillating this way as it's spinning, and just demonstrating how all this energy is conserved, and it doesn't make any sense to say this has twice the energy. Just doesn't make any sense. Yeah. I'll pause there and see if I can ponder any further. So I'm thinking of what experiment you can do with this, and you can't do much. So it's not that useful for trying to measure the exact forces, or to try to put energy into it, with the masses, because it's not enough of a mass differential. But in my opinion, it just demonstrates the point that this is angular rotation is just momentum. It's just a mass moving a velocity. That's all there is. Yeah. You You can, that's how light it is. You can just add a little bit of energy and cause motion. All right, so we'll pause for a moment and shall think about it some more. It is a couple minutes later and it's still spinning. Really quite frictionless. Five minutes later, still spinning. I was kind of waiting for it to stop and start rotating the other way. But I did have a thought. Okay, so I did say how this feels like nothing. I mean, just no energy at all. I mean, it's just nothing. I mean, I could just sit here and just barely, just any little tiny touch, and it, goes. But the trick is, it will get heavier and heavier depending on how fast I move it. So if I go faster than gravity can give objects weight, then I'm not going to feel, then I will feel the masses, and I will feel that I'm moving the masses. So the counterbalance thing only works if you move it slower than the time it takes gravity to create weight. So this goes back to kind of like the sliding over thin ice kind of argument, that it takes time for gravity to give you your weight. It doesn't happen instantaneously. You don't have any instantaneous weight. There's this, if I put you on a scale for a millisecond, you won't weigh your weight. If I put you on for, I don't know what the time would be, right? How many milliseconds it takes before you actually can weigh your actual weight. So if I moved you across a scale, if I put a scale inside the road or something and you're in a car and you're going across it, the faster you go across it, the less the car weighs. So you can't weigh your weight unless you give gravity time to give you your weight. So I think it's just an important fact to realize that if I move this slower than the gravitational force, there's almost zero energy I'm putting in. It's just such a tiny amount. But if I try to go faster, if I try to spin it, then I'm going to have to start moving these masses. I'm going to have to give them their momentum because they won't be counterbalancing anymore. They'll both be objects spinning. They both have linear momentum. That won't be a counterbalancing momentum. Yes, that was an argument I wanted to make was, there's talk about them. I think they're actually building this machine where they're going to create a lever inside a circular device and spin it to launch satellites. So instead of using a rocket, they're going to just create this huge amount of velocity and then shoot the rocket. And yeah, the idea sounds a bit wacky in terms of, there's going to be incredible forces, you could say on the fulcrum. But the trick is they have to counterbalance. So say the satellite would be the light thing further out on the arm, and they have a counterweight that's going to be spinning on the other side. And the catch is they have to release the satellite at exactly the same time they release the counterweight, or the whole thing, rips apart and blows up and flies across and, makes a horrible mess. Because they have to obey the equal and opposite reaction. They let a huge amount of joules of energy was released, and now they're stuck with it on an imbalanced stick. Okay, and that's not going to work. So it's just part of just another piece of argument you could make, that obviously you wouldn't be making such a device unless these momentum actually did work. Okay, and it's really what's going to decide is momentum, not kinetic energy. As you're spinning the counterweight and the satellite, you're balancing the momentums, not the kinetic energy. and such. I guess the further point being is it's just like this lever. The argument is if I have that spinning thing, right, and I was to shoot the counterweight instead of the satellite, the counterweight's going to have a ton less energy when it leaves, because it's going to have a much higher mass, much lower velocity. Its kinetic energy is going to be a lot slower, less than the satellite side. And how does that make any sense? That one side can produce 2,000 joules and the other side produces 25. I mean, you got to know that can't be right. That there has to be the same energy stored in both sides, or the whole thing would have spun apart. It has to have the same the same energy stored in both sides.